Thank you, Stephen, for your kind introduction. And so maybe at the outset, let me start and thanking Tatiana and Naharaju for their kind invitation. And it's pleasure actually to meet new French colleagues actually from France, as well as actually to meet the friends actually from India as well. So probably what I will do in the next 30 minutes, I try to talk about the experience and the journey which we actually end up in my independent career on cobalt, particularly in cobalt-3 oxidation state. So probably I will convince you at the end of my talk why the oxidation state actually really matters when you do organometallic chemistry. To start with, let's say 10 years ago, we try to ask questions actually when we try to do any chemical transformations. We need to pay attention to anything you add to the reaction flask, because eventually you wanted to actually transform your process or a chemical methodology from the laboratory to, let's say, large scale synthesis. Actually, any material which you add to the reaction flask actually matters. And what we witnessed actually over the last century is this particular transformation, right? This is what actually we witnessed actually over the last century, right? So what we perhaps actually going to witness maybe in our time or maybe in the future generation is actually going to be in this kind of a process. So which means actually you need to worry about what is the global problem actually does my research actually has to address in case if you want to address actually some of the bigger problems. And you also need to actually ask yourself a question, let's say, what is the purpose of that catalyst which you develop or the catalyst design which you would like to actually develop, and what impacts actually one research actually have a downstream ethical and investment actually driving applications, right? If you start to ask these actually fundamental questions in your independent research, perhaps actually you will take your academic research actually from the lab scale actually to the, let's say, a large scale synthesis. And that's the key questions actually came into play at the start of my independent career. So of course we always actually get inspiration actually from nature, right? Actually nature knows actually how to do things actually in a very sustainable way, right? Because the process has to go for a longer period of time. And if you actually work with something which is only actually available for a shorter period of time, then the process may not be sustainable. And that's why actually nature is quite different than us. And we always actually try to learn actually from nature and look at actually the metal which are used actually by the natural enzymes for various actually chemical processes. And these metals are widely available on Earth crust. And even if the process actually goes on for another 100 years, you may not be in a position to exhaust actually these metals, and that's the advantage of actually having natural enzymes actually utilizing these particular metals. I perhaps actually not to emphasize too much on the cost factor, so it is always actually there, but cost is not only the factor actually that matters. So 10 years ago, I started actually working on 3D metal catalysis, in particular actually focus on actually these three metals. And to start with, actually, we start with the two different actually topic. One is actually CH functionalization, and another one is a hydrogen neutral strategy. And of course, actually, with the time over the period, so with the knowledge which you gained in the topic, you started to expand the possibility of actually applying these knowledge in actually various topics. Perhaps it's the knowledge you apply, or perhaps the drawback which you actually have here, actually try to address actually through these particular topics. So for this talk today, and I would like to stay with only cobalt, and perhaps I would also actually try to convince you that whatever we try to actually do in our independent career, let's say with cobalt, is an exploration. I would actually start with. So this is a typical AXO process which we teach to an undergraduate students or actually let's say at the first year actually be chemistry students that a typical hydroformylation of an alkene into a corresponding, let's say, the carbonyl compound, and utilizing this hydrido-cobalt carbonyl species which is a low valent in nature. And the second example which I would like to bring in for the low valent cobalt chemistry is actually done by Murahashi almost 6 decades ago, where he has shown the utilization of the low valent cobalt can be utilized as a catalyst actually to coordinate with the imine first, and then actually bringing this ortho CH bond actually for oxidative addition, subsequently insert the carbonyl ligand, and followed by reductive elimination gives you this product. Then of course actually later the well-defined low valent complex actually came almost actually after 4 decades actually by Kish, where he has shown that stereoselective, that is trans-selective CH insertion happens actually with this particular CH bond, But the trans selectivity is not an inherent character of the catalyst. It is a cis addition followed by the isomerization actually will give you the trans product. And of course, a well-defined catalyst after this work is actually done extensively last 10 years by Mark Petit from Sorbonne, where he has shown a lot of low valent cobalt can be utilized for a wide variety of CC bond formation. And around 2010, I mean, this topic is quite intense, and there were 3 groups, Lutz from Germany and then Nakamura from Japan, were quite intensively working on making an in situ low valent cobalt complex and subsequently form the corresponding CC or a CN bond formation. But pay attention, they may have to use a stoichiometric amount of a Grignard reagent, which could be a base or a reductant. Okay? But understanding of these mechanistic investigation is rather not trivial, because it does forms a low valent species, and there is no clear idea about the species which forms in situ in these kind of reactions. So well-defined low valent complex, of course it's known based on CP star cobalt, and this is done by Maurice Bruckart some time ago, where he has shown that this low valent CP star cobalt can go for a clean atom economical 2 hydroacylation reactions with the vinyl silane and the corresponding aldehate. And this is what you have witnessed or shown in the literature, both catalytic and stoichiometric, for a low valent chemistry. But on the other hand, if you want to talk about the high valent chemistry, you do not technically have a sufficient examples in catalytic manner for a high valent cobalt. But we all teach to the undergraduate students that the Werner complex is the starting point for a coordination chemistry. And what is Werner complex is nothing but your cobalt 3. It's a super stable compound. You can isolate it, keep it on the table for 100 years, nothing going to happen to that. Such a stable cobalt 3 oxidation state is not explored on catalysis for many applications. It's always start with the cobalt 2, going down to cobalt 1 or a cobalt 0, rather start with the cobalt 2, going up to cobalt 3 or a cobalt 4, for example. So here are some of the examples where the cobalt 3 stoichiometric reactions were shown, where this is a cobalt 3 cyclometallic species isolated by activating this sp3ch bond using this multidentate ligand as a anchoring ligand. On the other hand, you start with the CP star based system or a CP based systems, where it's a cobalt 3 diiodate complex. Then you do the cyclometallation utilizing this azobenzene based directing group. And the third example, where you use the multidentate ligand again as a packet to put your metal in the middle and subsequently activate this proximal CH bond to get the corresponding cobalt cycle. That's a typical stoichiometric reactions where coordination chemistry would like to do to isolate these key cobalt cycles. But other than that, you do not have any examples known in the literature in terms of the catalytic reactions for a cobalt cycle. So like I said, so the last 10 years we have been extensively working on high valent cobalt or cobalt 3, cobalt 4. We don't go down to cobalt 2 to cobalt 1. And so we see there is an advantage and opportunity if you could start with the cobalt 2 combined with the photoredox, where you have the possibility of discovering new reactions. And so this was something which we have done recently, where the diene, which is typically a gas, for example 1,3-butadiene, which is not possible to access quite easily because you need to have the reactor to do the particular reaction. If you can somehow try to make this 1,3-diene surrogate in situ, then subsequently this 1,3-diene surrogate can be utilized by proton coupled electron transfer to make an allyl complex, and coupled with the various pi partners. In this case, for example, it's an alkyne, which will lead to the corresponding compound. We also demonstrate that you can do a sequential, let's say, an 3-carbon extension by starting with, let's say, the terpenol. You add a propagyl alcohol, you add one, you add a second propagyl alcohol, second, and the third propagyl alcohol. Go homologation as much as you want, like the enzyme does to make up to 45 carbon system, for example. And of course you can put, if you put a substituent here, eventually you put a substituent here, and you put a substituent here, you put a substituent here, which means it's typically a terpene synthesis like you do in the enzyme catalysis. But maybe today that's not the topic I really would like to discuss. There are two pre-catalysts which is utilized with the cobalt 3. One is, let's say, utilizing the CP star cobalt carbonyl bis iodide. When you use a CP star, you typically occupy the 3 coordination site on the top. Now what is left with is a 3 coordination site at the bottom. And because this is a CP is a very strongly coordinating ligand, which will not actually go out of the metal. And what you can play around with only these actually 3 ligands actually which is there underneath the metal. Now when you do the cyclometallation of the corresponding precursor, which will actually lead to this particular one, and if you do a comparison with the cobalt cycle and the rhoda cycle, you clearly understand that the carbon actually bound with the cobalt is a very short in nature because the cobalt is small in size compared with, let's say, the carbon bound with the rhodium, and due to which what happens to the nucleophilicity of this particular carbon is much more enhanced compared with, let's say, the nucleophilicity of the carbon actually bound with the rhodium. And of course, indeed, in majority of the examples when we try, we always actually try to see the comparison with the CP star cobalt and the rhodium, and we found actually the reactivity of the CP star cobalt in many cases actually is quite different actually compared with, let's say, the CP star rhodium. So that's why we always actually tend to say that the CP star cobalt have its own unique character. In addition, it can also emulate the CP star rhodium or iridium chemistry. So the second actually cobalt-3 chemistry, which also came into the same time around 2013, is the Douglas actually the in situ formed cobalt complex, where you start with the cobalt-2, you add actually manganese stoichiometric amount, you also add a pyrrolate stoichiometric amount, you utilize the bidentate ligand and form the corresponding annulation product. But trust me, at that time when this paper actually came in, the understanding of actually this in situ formed cobalt cycle is not actually well known, or it is not actually well understood at that point in time. Later, actually, so our group and Walla and Debu actually from Bombay, they showed actually in both the cases actually we showed this particular cobalt cycle is possible for us to isolate. And in the case of actually Debu, where he showed actually methanol is actually comes at the 6 coordination site. And in our case, we showed actually that the isonitrile comes at the 6 coordination site, clearly indicates that the substrate behave like a tridentate and a bidentate ligand with the solvent actually coordinates at the 6 coordination site. So if this is really true, that these particular ligand which is actually come from the substrate behave like a spectator ligand, and the one actually which forms a metallocycle will further actually goes and bind with an alkyne in this case, for example, subsequently do the migratory insertion and reductive elimination will actually lead to this particular product. But of course, when Douglas actually published this paper back in 2013, it was not actually well understood. It's an in situ formed compound which actually lead to this particular product. So to convince you that actually we did, it is possible actually for us to isolate actually such kind of a metallocycle, and that can be applied actually for a wide variety of actually transformations actually which could be accessed actually utilizing CP star cobalt as a pre-catalyst. But the entire catalytic cycle actually operates through the cobalt-3 oxidation state, and it doesn't actually go at the low valent unless in some cases where the reductive elimination happens, liberates the cobalt-1, but you do not actually need an oxidant actually in order to perform this particular reaction. So of course, when you do work with the cobalt compared with the rhodium and iridium, there is always a question comes that is there any actually single electron transfer reaction happens, or is there any radical involvement happens compared with, let's say, the 4D and 5D, because 4D and 5D typically the reactions are 2 electron transfer, and in the case of 3D metal it could be 2 electron, it could be 1 electron depending on the reaction conditions, right? So we do take the observe in the case of CP star cobalt, the behavior of the catalytic cycle is similar to CP star rhodium and iridium. And we could isolate in these cases, for example, you start with this cobalt cycle, add an alkyne which actually goes for a migratory insertion, and we get this 7-membered alkenyl intermediate, and that is actually goes for a proto-demethylation, will give you the corresponding vinylated product, or it goes for an annulation, actually you end up getting such kind of an annulation, for example. So which clearly indicates actually that this is a catalytic intermediate which is involved in the catalytic cycle. I mean, typically you isolate the metallocycle, but in this case we isolate the one after migratory insertion, gives you the corresponding 7-membered alkenyl intermediate. People always say the CO which is actually there originally at the catalyst actually goes out. No, the CO is still actually inside your solution and it is bound to the catalyst. Okay, so when you actually try to do the stoichiometric reaction, say the CO is still there in the solution. The second metallocycle which actually forms in this case is nothing but your octahedral cobalt complex, and this octahedral cobalt complex will have actually the corresponding tridentate and the bidentate ligand, and we parallelly actually try to do the transformation actually with this particular catalytic system utilizing the bidentate ligand, and where we also actually try to show various cyclic transformation utilizing actually this cobalt-2 systems. And we isolate actually the corresponding metallocycle, like I said in this case, where you can clearly see the linear coordination of an isonitrile at the 6 coordination site clearly indicates actually that this is the intermediate actually which formed actually in situ in your reaction, and indeed actually this particular one is also catalytically active. It's not actually going through the resting state. So this actually culminate our effort actually both cobalt 3 with the CP star as a pre-catalyst, or cobalt 2 in situ you form the cobalt 3 metallocycle that lead to the corresponding transformations. So of course, when you start, the field actually started to be crowded, and at the beginning it was not actually possible for you to understand the mechanism in detail. But once you actually start to understand the chemistry is actually quite well possible with the CP star cobalt catalyst. And so there are many actually contributions come from various actually groups. Even beautiful contributions actually come from let's say Madhu actually, who has shown how a weak chelation actually has been a powerful actually tool actually to do a CH functionalization rather than the strongly chelating interacting group. In the recent work he has also actually shown how a multi-arene compounds actually can also be accessed actually very easily actually utilizing actually the simple CP star cobalt catalyst. But as I said, actually when you start an independent career, you will actually have a very small group to work with. It's always actually difficult. So, and that's why you need to actually start to be different. Otherwise, you will get lost in the group, where people are actually more focused on actually sp2-CH functionalization. At that point, we ask a question: can we actually move away from sp2 to sp3, because it's rather actually more difficult compared with sp2? And if that actually happens, we should actually form such kind of a metallocycle, and that should actually lead to the corresponding actually product, right? So our effort actually in this direction came actually very early, where we shown actually that utilizing this pyridine as a directing group, you could do in situ the corresponding metallocycle, and that metallocycle will actually coupled with the pi partners actually gives you the corresponding product. So we clearly show the CH bond is inserted actually between the metal and between the carbon and the hydrogen, and stereoselectively end up in getting this 8 allyl actually quinoline through a CH activation process. We also actually try to understand the activation process. So what we know with the sp2-CH, where the carboxylate actually originally bound with the metal is the one actually picking up the proton and do the CMD process. And in the case of sp3, it is not the carboxylate originally bound with the metal actually picks up the proton. It is the carboxylate actually comes outside the coordination sphere, comes as a base, comes and picks up the proton and goes and makes the corresponding CMD process. So this is quite actually different than the one which you observed with sp2-CH functionalization. Of course, when we do the scope actually, we realize that the moment you put an R group, it doesn't work, which means actually that the terminal sp3-CH bond is possible to activate, and the internal sp3-CH bond is not actually possible for us to activate, at least with this particular catalytic system. So which is also complementary, because in a radical chemistry where the tertiary or a secondary radical is more actually stabilized compared to the primary radical, so the primary CH activation actually with the radical chemistry is very difficult compared with, let's say, the metal catalyzed process. So this problem was there actually at that time with our lab, and we came across actually 2 papers actually came at the same time actually when the work was actually going on in our lab. So one is a work from Heboji, where he has shown this intramolecular CH amidation to form the lactam. The other one actually from Zhang group, where he has shown actually that this exocyclic olefin formation by sigma activation of the corresponding CH bond actually ends up in getting the corresponding 5-membered cycle. So if these 2 reports are true and their outcome is true, then one should actually go through this kind of intermediate. If this intermediate is actually possible to access in the catalytic cycle, then the very simple one actually one can think of is actually introduce the CO in the reaction mixture and see actually what happens if this actually CO can actually insert between the metal and the carbon. If that actually happens, then eventually reductive elimination actually gives you the corresponding, expected actually product. So to make the story start, actually, let's say this is optimized the condition we utilize, and we can show wide variety of actually, let's say, carbonylation is possible with the sp3-CH bond, and you can even actually do cyclopropane as a starting material and do the corresponding carbonylation where the cyclopropane doesn't open up. So which is clearly an interesting compound actually to see. And you don't need to have the tetrasubstituted carbon always here. You can even actually start with, let's say, the simple propanamide, alpha methyl. And you could also actually activate the internal sp3-CH bond, which was not actually possible with the CP star catalyst, and now it is actually possible. So at that point, we ask a question: so can we move away from CO to CO2? If we use a CO2 as a CO source, this will be even more interesting, because CO2 is inert first, it's very difficult to activate, and the second, it is much more actually cheaper compared to the CO gas, and it's not toxic. So if that actually happens, then you are actually talking about a thermodynamically unfavorable process. You start with the inert substrate, you combine with an inert actually starting material to form a product which is actually thermodynamically not allowed. So what you actually try to do in the process, you try to do the reactives, inert substrate into a reactive organometallic intermediate. You convert the CO2 into CO via plugging up the oxygen actually from the CO2. Then you actually talk about actually two reactive intermediate actually in the reaction pot, and eventually actually gives the corresponding carbonylation product. So if this is the one actually which we would like to access, we thought of actually utilizing this two chamber system, where in chamber A you produce the corresponding CO gas actually from the CO2 and trap the CO gas which is generated in chamber A in chamber B by trapping the gas actually which is generated in the chamber A, for example. So we utilize actually this two chamber system actually to make the carbonylation with the knowledge which accumulated with the sp3ch and applied actually with the CO2 as a CO source actually to do the carbonylation. For example, the reaction condition shown here clearly indicates that if you change the condition in chamber A or a chamber B, your reaction will not actually work, or it is not efficient. So that means all the controlled experiments were shown clearly indicates that the chamber A conditions and the chamber B condition has to be met, otherwise the chemistry will not actually work. So you can do the phthalimide synthesis, you can do a saccharin synthesis, you can have a wide variety of heterocycles at the backbone, clearly indicates that it is very selective, and most of the case in the CH activation chemistry, when you have a heterocycles, you direct the CH on a different occasion. So in this case, for example, if you have a heterocycle, you have the possibility of activating this CH. If you have a heterocycle, you have the possibility of activating this CH, but this is very selective to go at the bidentate glycylation site rather than the monogonate glycylation site. So this is why the reaction actually gives you the corresponding product, and this allows us to buy the commercially available pharmaceutical drugs and then actually try to install your directing group and then do the carbonylation at a very particular site, and that actually produces the corresponding carbonylation product in a particular CH bond over the rest of the heterocycles which are present in the molecule. Of course, the chemistry can also be extended to sp3, not only sp2, because we already established the sp3ch carbonylation. So we could show that actually it is indeed actually possible. I wanted to actually emphasize the fact that the carbonylation reaction which was actually shown by Murahasi in 1955 requires 150 bar pressure of CO gas to do a carbonylation with the cobalt catalyst. And what we do here is the carbonylation reactions with the balloon pressure. Okay, typically at 1 atmosphere pressure, and that's exactly what allowed us also to transform from CO to CO2, because you only need 1 to 2 equivalent of CO gas. You don't need actually 100 bar pressure or 50 bar pressure or even 10 bar pressure. You just need 1 to 2 equivalent of a CO which needs to be generated in situ, and that is sufficiently good enough to do the carbonylation here. So this culminate our effort actually on one side actually with the CP star cobalt, where allowed us actually to show that it is indeed an LX ligand actually bound with the cobalt actually gives you the corresponding cobalt 3. If this is really true, you can in principle actually replace this LX ligand with any ligand which you would like to. Right, that allow you to get well-defined cobalt catalyst. Say for example, you can use an LX type ligand of this type and an amino acid or an amide or an hydroxyquinoline, or you can even actually use a CP star, tertiary CP star. You can prepare a large variety of a well-defined cobalt catalyst at will. On the other side, which is actually again quite interesting, as I told you before, these two are coming from the substrate itself. One is a tridentate ligand upon CH activation, and another one is a bidentate ligand coming from the starting material itself, right? If you can somehow replace this actually innocent ligand which is actually staying there as a anchoring, it's only to actually satisfy the coordination number. Otherwise actually it has no role actually here. If this is really true, can we try to actually replace this ligand with, let's say for example, 8-hydroxyquinoline? Of course we come to this particular ligand because we already gain quite a bit of knowledge on this when we make this particular complex. And you could actually replace this with the NO or an NN, or let's say even actually let's say chiral ligand for example. So to try our test, so for example this is the intermediate which we form when we do a CH amidation chemistry, okay, where the cyclomethylated cobalt will actually form a nitrene species, subsequently go for migratory insertion, will give you the corresponding CH amidation product. Now replace this nitrogen coordinated cobalt cycle with, let's say, an external ligand. Now this forms an LX coordination. Now you form the same nitrene species. If this is really the case, and you should actually make a corresponding complex which are structurally characterized in all the cases. You can use CP star, CP, phenyl CP, biphenyl CP. You could even actually modify the ligands actually at will the way you would like to, and you can also actually isolate actually all these complexes. All of them are structurally characterized, and I would actually say probably only 2% of actually the complexes which we isolated are published by us. The rest of them are still stays in the lab, because unless actually we find an application, we can't actually really publish those sections as well. So to convince you that actually we have a library of actually cobalt-3 complex in our lab, and we try to actually screen which catalyst is active for what. And when we tried this particular catalyst, with the alkylation chemistry, we found out that the C alkylation of this alpha CH bond of the ketone very selectively goes, and eventually you will end up in getting the corresponding C alkylation utilizing secondary alcohol as an alkylated source, for example. So what we also observed that, so this pentamethyl group, sometimes actually tricky, because people say, okay, then you are restricted actually for an application in case if you do an alkylation of a ketone with a pentamethyl, which is not really true, because this pentamethyl arene forces actually this acyl group actually in a orthogonal manner. So because of which what happens that you can do a radical cleavage, and when you do the radical cleavage, you can trap it actually with any nucleophile you want. So in principle actually you do post modification after an alkylation actually to the chemistry which you would like to. Now this particular chemistry was interesting to us at that point, not in terms of the reaction outcome for methodology, in terms of the mechanistic understanding, because what we found here, these particular catalysts do not actually produce the corresponding, let's say, the hydride complex. Rather actually it produces the 2-electron transfer, which means actually you are starting with the cobalt-3. It cannot actually go to cobalt-3 to cobalt-5 or a cobalt-4. Rather actually what we found is that the alkoxy species which is actually formed here does not go for a beta hydride elimination. Rather actually the phenoxy which is bound with the metal act as a base, abstracts the beta hydrogen, and eventually you end up in actually producing the cobalt-1 and the corresponding aldehyde. Okay, what we know in the literature is typically an oxidative activation or an ionic activation of the metal hydride chemistry, right, where you do H plus H minus transfer or a 2-hydride chemistry transfer. That is what in the last 5 decades actually in metal hydride chemistry is known. What is not actually known or what is not explored is the reductive activation, where you reduce the metal by 2 electron and transfer 2 proton actually to the substrate, which is not actually known, and that's what actually we observed in this particular chemistry. So perhaps actually I'm not in a position to show that actually more in detail, because I would like to show only on the CH actually for today's talk. So these are 2 reports came in. So this was actually published by us actually before pandemic, and this the 2 report actually came in from Sukhbok Chung group actually during the pandemic, where our labs were shut down actually for 8 months in 2020 and 7 months in 2021, completely shut down. There is no one is allowed to go to the lab. And during this time it was frustrating to see catalyst which was actually used by us in the lab utilized by Sukhbok Chung and shown actually that intramolecular CH amidation and intermolecular CH amidation was actually possible utilizing the CP star cobalt actually chlorocatalyst. Okay, the only difference in the case of Sukhbo is he start with the chloro and we start with the iodo. Okay, that's the only difference. But if you really look at the system, whether you start with the chloro or start with an iodo, you form a nitrine species. Right, and once you form a nitrine species, you are in cationic catalyst. You are not a neutral catalyst anymore. And it doesn't matter whether you start with the chloro or iodo, right? So which means actually that species actually which formed, whether you start with the chloro or iodo, should actually give you the corresponding product. So since we had actually all these catalysts in hand, I asked the student actually test out actually whether the reaction which was shown by Sukhbok is actually possible with our catalyst first. And indeed actually when he tried the reaction with the CP, no reaction. With the tertibutyl CP, he gets the product. With the CP star, he gets the product. With the dichloro, he gets the product. With the nitro, he gets the product. I want you to pay attention. In the case of dichloro, the reaction works. When he don't have a dichloro, the chemistry doesn't work with the Sukhbok. And when he gets a nitro, the chemistry works. When he doesn't have a nitro, the reaction doesn't work. So he clearly sell this particular one, saying that via electronic modification of the ligand, he was able to actually attain the product. But that's not really true, because when we see here dichloro, nitro, let's say even the simple NO, there is no modification, 94, 95, 84, there is no actually much difference in terms of the reaction outcome. As I said to you before, if this is the intermediate which forms in situ, it doesn't matter you start with the chloro or iodo. And when we see the scope, the chemistry indeed actually works. for intramolecular CH amidation, like it was shown actually by Sugbok. But I believe in his case, the chemistry operates through a different mechanism where the chlorine which is actually goes out of the system is still in the solution and the chlorine is not innocent. And the chlorine actually behave like a HAT chemistry, comes and actually picks up the proton, and that's how the activation happens. And in the case of IDO, it is not the case, and that is why you do not actually see any difference actually between the simple NO versus, let's say, the substituted NO as a catalyst. Now this allows us actually to show the monodentate ligand, and this also allows us actually to show the bidentate ligand by replacing this, because we gain a knowledge that the NO ligands are better than the NN ligand, and eventually you form the corresponding NO complex. Now, last few minutes I would like to actually show that the knowledge which we gained on the NO ligand allowed us actually to expand the knowledge actually on the octahedral complex side, where we shown actually earlier that it is indeed possible actually to get such kind of a product with the benzamide, and when we try to do the reaction without an external ligand with the phosphoramide, the reaction doesn't work. So, and then we started to add a ligand, and we found out that when we add actually this as an external ligand, we are able to actually get the product actually with the phosphoramide. And indeed actually the selectivity what you get in the cobalt chemistry is always the arene group or alkyl group actually goes on this side, and when we do the reaction with this actually we found out it goes on the opposite side, so we call that as an inverse reduced selectivity. And indeed actually the reaction works. We were able to isolate actually all these compounds utilizing this NO as a ligand. And when we try to do this chemistry, we, like I said, actually we replace actually, one of the bidentate ligand with the external ligand. We form this actually form the metallated cobalto cycle, and eventually this cobalto cycle is a key intermediate to get the corresponding compound. So we felt at this point, if this is true, in situ this particular complex is formed, we should in principle actually transform this particular one with a chiral ligand, for example Salax. If that actually happens, your situation is complicated. What is that complicated? Now you start with the chiral ligand, you have a chiral source 1. Now upon actually CH activation, your metal is chiral, right? So that means you actually started to end up in diastereomer. Now worry about, you have a possible optical isomers, you have a delta and tau. Now worry about your geometrical isomers, you have facial and meridonial. You have a possibility of at least 6 to 7 chiral isomers or optical isomers, and the diastereomers you can actually multiply with respect to the number of actually chiral packet which is actually there in the system. So that will lead to something like a 20 possible diastereomers actually which can form in situ from your reaction mixture. That's absolutely scary, because if you form 20 possible diastereomers, it is extremely difficult for you to get a highly inertial selective reactions. But somehow the system knows actually how to do it. And so these are the two examples which are actually shown with the CP system, where one is actually utilizing the chiral carboxylic acid, where you had to really make a bulky carboxylic acid in order to achieve the ER up to 90%. And this is a CP binaphthyl based CP by Kramer. I can tell you that if you want to synthesize this particular binap CP, you start with, let's say, 20 gram, you end up in getting 100 milligram. And then you know very well that this is not actually an active catalyst. You go back from the starting. You cannot actually modify the as precursor, okay, which means it's a laborious, it's not actually something very easy, although the chemistry looks interesting. So to make our story start, actually we start to screen the simple Salax ligand in situ, and eventually we get the high inertial selective transformations via annulation, where you do the disymmetrization of the phosphine upon actually CH activation. And in most of the cases, the substrate scope is actually quite interesting. We get almost actually 99% EE in most of the cases. And absolute stereochemistry is actually confirmed actually by crystal structure. So to allow us actually to have both the possible isomers depending on the R or S ligand, actually you start with actually with the Salax. And in the case of actually, let's say, the phosphoramide scope, we can have various actually functional groups at the backbone, absolutely no problem. I want to pay attention that because we use the sodium pivylate as a base, and that actually comes and sit in this particular position, we don't actually add any other nucleophile. And when we try to replace this bulky sodium pivylate actually with this or with this, the chemistry still works. The moment actually you replace this bulky carboxylate with the acetate or a benzoate, absolutely no reaction. But pay attention, first actually no reaction because these bases are not good enough to do the cyclometallation. And second, because there is no reaction, obviously you will not actually look at the enantiomer selectivity as well. So we did actually try to isolate the corresponding cobalto cycle. Here is a cobalto cycle isolated, and we were structurally able to characterize. And the moment you are structurally able to characterize, you can say whether it is facial or meridonial. You can say whether it is delta or tau. You can also actually say the corresponding, let's say, the chiral ligand which you start with. So in principle, with this, actually, let's say the pre-isolated actually catalyst, you perform the stoichiometric reactions, we were pleased to get the corresponding vinyl bromide. Like that's a vinyl bromide. One would expect, okay, the vinyl bromide actually perhaps actually goes for a ligand exchange with a pivalate, and eventually you might actually end up getting the pivalate as a compound. And when we set out the reaction, let's say by treating with the sodium pivalate, no reaction. That means it's still a metal involved actually transformation. And under standard conditions also no reaction, which was puzzling to us. At least if without a metal no reaction, understandable. But under standard conditions, the vinyl bromide should be transformed. So, but we then actually realized that under standard conditions we start with the cobalt 2, we don't start with the cobalt 1. So I said actually to my student that okay, maybe you start with this along with an additional starting material. Now you do the reaction. Now what happens when you add the CH activation, in this case you generate a low valent cobalt 1, and that low valent cobalt 1 perhaps actually goes for oxidative addition with this, and then actually do the pivalate actually via ligand exchange will lead to the product. And when he do the reaction by taking these two together, and he ends up in getting both the products. So which clearly indicates that you had to generate somehow actually low valent species in situ in your reaction, otherwise this transformation will not work. Of course, when you submit a paper, your reviewer always actually ask a question, okay, what is the use of this guy? Okay, fine. You do the transformation, selectively show that, you start with the 98% E, you end up getting 97% E via, typical Suzuki coupling utilizing, let's say, the nickel as a catalyst, for example. So, like I said, actually, initial ligand exchange will actually lead to the cobalt 2, subsequent 1 electron oxidation cobalt 3, which will actually then, replace actually the solvent actually at the 6 coordination site. Alkyne comes into picture. Now the question comes is that depending on the alkyne insertion, you can actually go for a 2-1 insertion or a 1-2 insertion, and if it is 1-2 insertion, you end up in getting this intermediate, and subsequently go for a reductive elimination, gives you the vinyl bromide, which we studied actually in the stoichiometric reaction. Now the liberated cobalt 1 goes for oxidative addition, you end up in getting this scenario. Now this one will actually go for a oxidative addition because this is cobalt 1, and that cobalt 3 do a ligand exchange with the pivalate, eventually actually gives you the product, and then get back to the cobalt 1, which will actually goes on actually for the catalytic cycle. Now the key question asked at this point is that who is the active guy and what is the energetic level? In the case of, let's say, the cyclomethylated species, we form actually delta and tau. So we clearly indicate that the one is actually lower in energy over the other. And the second question is actually what is the migratory insertion step? Is it 1-2 or a 2-1? It's clearly indicate that the 1-2 insertion is actually much more favored actually versus the 2-1 insertion. And the resolution of the phosphorus also clearly indicates that the one actually scores over the other, and that is why we end up in actually getting that clear resolution. So just to actually convince you that the chemistry is interesting, but there is a problem lies with this chemistry for a too long period, and people do not actually bother to address. Of course, actually there are numerous papers comes into this time, but you don't pay attention. So when you do this cobalt 1 to cobalt 2 or a cobalt 2 to cobalt 3, you have to use a manganese as a oxidant or a silver as an oxidant. Without actually manganese or a silver, the chemistry doesn't work. That's not the case typically with the ruthenium 2, rhodium 3. You use a copper as an oxidant and it works effectively, for example, because that's a 2 electron oxidation. Here it is a 1 electron oxidation. So if it is a 1 electron oxidation, why not to replace this actually with the stoichiometric amount of silver or manganese with the photocatalyst, because that should actually eventually do the job, right, with the sign of light. So if that actually happens, then you end up in getting the corresponding cobalt 1 to cobalt 2 or a cobalt 2 to cobalt 3, for example. So, like I was discussing during the break, that I am not a guy come from the photophysical chemistry background, and I don't actually have any experience in the past actually work on photocatalysts. And if I have to really screen all the photocatalysts which are widely available in the literature, it is going to be extremely difficult task. First, you have to be rich. Your lab has to be rich to buy all the photocatalysts, and second, it may be an extensive task actually to screen on the photocatalyst. The very simple way to actually approach, if it is an electron transfer or energy transfer, if you understand this, what is your need, then you go by that. So in this case, it's an electron transfer. So we found out that the oxidation potential of the reduction potential of the photocatalyst should actually match with the oxidation potential of the cobalt 1 to cobalt 2 or a cobalt 2 to cobalt 3. If that actually happens, then that's the right choice of the catalyst which you would like to use. So these two are the right candidate actually for oxidative addition, and eventually actually we end up getting the corresponding annulation product. And so to show that actually now we don't need a manganese or a silver, and you can actually do the chemistry with, let's say, the photocatalyst. And you also have the corresponding actually two cobalt actually isolated species to show that it is working with the alkynyl bromide. So it is actually possible to extend. So we recently show the asymmetric version of the same. Now, because you combine photocatalyst along with the cobalt, so in this case, actually, we do actually the photocatalyst combined with the cobalt and show a possibility of an asymmetric, let's say, a dearomatization reaction using indole as a starting material, as a pi partner, where we show this fused actually pi cyclic system with this actually benzamide as a starting material. And in this case also, we try to actually understand the corresponding cobalt cycle and the corresponding delta and tau energy level to convince the reviewer that it is indeed actually possible. And of course, there are a lot of actually non-covalent interactions involved in the cis species actually which you form, where you have a lot of actually pi-pi stacking occurs actually between these two, for example, and that's how actually it stabilizes the one intermediate over the other. To show the last example is, you have the diaxial is actually typically very well known, which well explored, right? Especially when it is actually in a close proximity, right, at the vicinal position. The moment actually you put this diaxial at the next position, it is very difficult to control, and most of the times such kind of a diaxial is actually very rare and explored in the literature. So we recently actually found that it is actually indeed possible to have a diaxial at the not at the vicinal position, but let's say at the distal position, where you are able to still control the double CN atrope. Usually what is known is a single CN atrope, CC atrope, like actually in this case diaxial. The double CN atrope is more challenging, and I don't see any example in the literature for a double CN atrope. And here actually we could able to achieve a large variety of substrates actually with absolutely stunning enantiomer selectivity. And in the absolute stereochemistry of this chemistry is also actually possible to confirm by the crystal structure of the corresponding product. And to show the substrate scope actually both at the indole side as well as the amide side, it is indeed actually working. I also wanted to actually tell you that when we do this chemistry, there is a drawback. The drawback is the directing group. Yeah, I'm done almost. The directing group, because the directing group is always there, and the question actually is, what do you do with this directing group? If you can actually somehow remove this directing group, this will be very useful. And here is an example we show. The directing group is actually cleaved in situ. You don't have any more directing group attached. Previously what I showed is the distal diaxial. Now the directing group cleaved in situ, and you actually got the corresponding, let's say, the single actually CN atrope actually chirality with absolutely high enantiomer selectivity. Now this actually gives us a wide possible opportunity actually to synthesize many useful actually compounds which you would like to. So here I also wanted to emphasize that I don't need any metal oxidant. I don't need a photocatalyst. I just need to do the reaction under open air in a flask, and just a air is sufficiently good enough actually to oxidize it, to make it actually enantiomer selective. So with that actually I come to a conclusion where I showed actually by simply understanding the cobalt cycle, you are able to actually make a large variety of well-defined cobalt 3 catalysts. By understanding actually the cobalt cycle, let's say with the cobalt 3 with the octavortal complex, we are now able to actually replace the racemic ligand with the chiral ligand and show the power of actually asymmetric catalysis and cobalt 3 chemistry. So of course none of this work is actually done by me. It's all actually done by my students, and high respect actually to them. And so I also actually thankful actually to collaborators actually on various projects actually we work with. And finally I also would like to actually thank the funding agency actually for the generous support. Thank you so much actually for your kind attention, and I'll be happy to answer any questions if you have.
Thank you so much for this wonderful journey in cobalt 3 catalysis. I'm sure there are some questions.
Yeah, fantastic talk, Basker, as usual. So I have a question related to the last part for the diaxial system. So you have the CN atropo selectivity. Can you please comment on the origin of diastereo selectivity in that process?
So again, the key is actually to form the chiral metal cycle. That's my still feeling. I believe that once you resolute the metal upon CH activation, it's chiral throughout. Okay, yeah. Even if the substrate actually goes for reductive elimination, it is still chiral, which means, let's say, typically when you do a coordination chemistry, once you form the delta tau resolution and you separate actually delta and separate actually tau, and then you take the delta alone as a catalyst and do the chemistry, you will not actually do the racemization. And that's exactly what happens here also. Once you form the cyclometallation, your metal is at chiral. Even if the Salax ligand goes out of the metal, I will still actually do the chiral catalysis, because the ligand can go and come back. Yeah. Even the chiral ligand.
So ideally you have 2 axes, 2 points of chirality, right?
Exactly.
So strictly speaking, for stereoisomers are possible.
Yep.
Out of them, 2 are diastereomers.
Yes.
I understood the origin of enantiomer selectivity, but the origin of diastereo selectivity.
I think the key is actually this phenyl. Because this phenyl, I mean, if we replace this phenyl with an alkyl, we lose the diastereo selectivity.
Okay.
Okay, this phenyl is actually goes, if you can see the crystal structure, this goes actually in between.
Okay.
And we do have actually a pi-pi stacking between actually this particular phenyl group and actually this particular group.
So that phenyl is restricting the CN bond rotation as well as the
Other actually
quinol.
other CN bond rotation, both.
Okay.
Double CN rotation. And we don't need to put any ortho group here, for example.
Yeah, but that is restricting the rotation around the CN bond, right?
Yes.
That is controlling the enantiomer selectivity.
Yes.
But my question is about the diastereo selectivity. I hope you understand.
Yeah, I understand, but I don't have any explanation at this moment. I mean, but I believe actually, this is, as I said, actually, it's not a simple, only steric actually that comes into play. There is also actually non-covalent interactions, like I told you before. There are actually pi-pi stacking occurs at various positions in the catalytic cycle. I mean, in the intermediate which you actually propose.
Did you determine the rotation barrier for the CN bond?
No, I didn't. I mean,
Probably could be a possibility you get some information about which is controlling the CN rotation and things like that.
okay, that's a good point. Thank you.
All right, thanks.
Next question.
Thank you. Very nice talk.
Thank
I
you,
really
Tim.
like the last part as well. So I was curious to know, how did you cleave in situ the directing group?
So in the case of actually, let's say the last part actually where we utilize the NN actually bond as a oxidant actually, which allows us actually to in situ cleave and win the reaction itself. I mean, at the end of the reaction actually we only see the product actually without having the directing group.
Okay.
It's not actually we do the directing group removal actually as a next step. No, in the same pot itself actually the NN bond actually get cleaved.
The NC bond, right?
No, in the case of actually this is an NC bond. I mean, the starting material in this case is not actually NC bond. This is actually, this is quinoline and this is actually quinolone.
Ah, okay.
So it's different.
Okay.
Because, I show this because this is a continuation of the same chemistry, same CN atrope. I have experienced that actually from the reviewer that can you remove the directing group? This question is actually always bothers me. So then we said no, unless you remove the directing group, we cannot go forward. Then the student actually spend some time and find the conditions where the directing group is actually possible to cleave and you are able to actually get the compounds actually, let's say for example something like this.
Yes.
Right, so it's quite easy and very. I think now this opens a lot of possibility for me.
Yes, and I have a naive question because now you have like 2 CN bond axial isomerism. So, do you think you can maybe try it with other heterocycles like sulfur-containing one? Do you think it might be something you can do? And ideally, you might end up with sulfonium that will be like a real synthetic platform afterwards.
The work is currently going on.
Thank you.
Yeah.
Okay, thank you. Any other question? One last.
Yes, Anis.
Very nice talk. So when you did the chiral phosphine oxide, so have you tried to reduce the phosphine oxide if your compound are stable or not?
If my compound what?
If the phosphine...
Phosphinamide, yeah.
Yeah, so you have the phosphine oxide. So if you reduce them, the phosphine are stable in the air?
Oh, I mean, after taking the product, actually try to reduce it.
Yeah.
No, we did not do it. So I see examples in the literature, but in this example, we did not do it. But I believe it's possible. If you use a chlorotrisilane, it's possible. Trichlorosilane, sorry. Yeah.
Hang on.
So we have to use the racemic ligand, which I showed you before. We start with 8-hydroxyquinoline as a racemic ligand. Okay. Yeah. But there are also actually reactions in this chemistry. The background reactions doesn't require a ligand. You can also do the same because in the last 10 years, cobalt-2 chemistry, no additional ligand, right? It's all actually background reaction where the substrate itself acts as a tridentate and bidentate. So you don't need actually some.
The diastereoselectivity of the racemic reaction also same. It's a 1 diastereoisomer.
That's a good point. I did not actually ask.
That is actually I want to know. Like.
Oh, that's a good point. I did not actually pay attention to that. Yeah, maybe.
That you can easily check from the HPLC, right?
Yes. I can cross check, but I have not
I believe
cross.
that would be a single diastereoisomer. I just guess.
I think so. I mean, otherwise, actually, now you end up in getting it's a structural, I mean, conformation actually which lead to the single diastereomer. It's not a catalyst driven. That's my feeling.
That is what I was thinking. Like
Yeah.
the product is there.
Okay, thank you. I think we have to. It's passionate in discussion. We can go on afterwards. So we go on next speaker, and our next speaker is Aurélie Clara. So Aurélie.
Long live India and France friendship.